So here I'm back in R. I'm going to fit a full tree again with CP pretty small, 1e to the minus 10. That's a very small value of CP. I'm going to call a function which is then going to iterate through loads of different values of the complexity parameter. It will start off with the complexity parameter as small as it was, but it's then going to prune the tree. It's going to increase the complexity parameter slightly, and every time it increases the complexity parameter slightly, it will see, is it still worth keeping all of these leaves? And the answer is going to be probably not. Some leaves on the tree won't be worth the penalty. When CP is very small, there is no penalty or no significant penalty to each leaf. But imagine if one leaf only reduced the mean square error by 1e to the minus 9. When we increase CP so that it is now 1e to the minus 8, that leaf is going to disappear. Good, so we've gone through 588 different values of CP. Let's plot them. Well, I have to say, it looks like it's meant to look, but it's not very impressive. You can see that the loss function on train is improving all the time till it has an MAE right down at the bottom of 4,000, whatever we thought. The validation loss function, on the other hand, goes down to a minimum somewhere over here, and then it starts going back up again. So it is true that we can find an optimal trade-off, but at that optimal point, the performance is nowhere near as good as our best linear model was. What we should do, and what we've typically done in the past, is once we've found the optimal complexity parameter, having split our train data into two, train and validation, we're going to fit one last model with the optimal complexity over all of our training data, train and validation together, and we will find the performance on the test data. Here we have it. The best performance we can get out of a decision tree is 16584 on train, but on validation, but on test, 21499. That is pretty rubbish. Is our best decision tree good? No. Is it as good as penalized regression? Nowhere near. What are the hyperparameters of a decision tree? Can you think what the hyperparameters are? You should get at least one. We've been talking about it all the time. The complexity parameter is certainly a hyperparameter, but there are other ways to tune the complexity of a decision tree. We could insist on there being a larger number of observations in each leaf, and we could insist on a maximum depth, so a tree can't go beyond a certain depth. Tuning leaf size can reduce overfitting. Why? It feels obvious to me, and when things feel obvious to me, I'm not normally very good at explaining them. But if you think what happens here, we are going to make predictions based on our decision tree, which we have fitted over the training data. If we allow there to be only one house in a particular leaf, it means that any future house that falls into the same leaf as a result of going down the decision tree, the prediction for that future house is going to be made based on just one other similar house. Now, yes, it might be similar as far as the information we have in the decision tree is concerned, but predicting anything based on just one example seems like a really bad idea. It seems to make sense that as we increase the number of examples we insist on having in each leaf, we will get less noisy predictions. If we do it too much, we'll obviously get just an intercept-only model, because we'll insist that all of the data has to be in the leaf. So here's a bit of R code, which is going to try a few different leaf sizes. Here we have some results of trying to tune the minimum split parameter. On the right side over here, the minimum number of houses we have in each leaf before we're allowed to split the leaf is 2 to the power of 10, which is probably not short of the full amount of data we have, or is probably the full amount of data that we have in our model. And you can see train and validation error are the same, and they're huge. However, there is a sweet spot over here somewhere on the validation curve where the actual minimum number of houses in each leaf is 2 to the power of 5, which is 32. That doesn't sound particularly stupid to say that if we're going to predict what a house might be like, we want to look at 32 similar houses which fall into the same leaf after making the various decisions about the size, the number of bathrooms, and the number of bedrooms, and so on and so forth. I have over here something to try and show the interplay between these two different hyperparameters, the number of observations you must have before splitting and the complexity parameter. And what we see is that the optimal complexity parameter reduces as the minimum split gets bigger, because, as my note over there says, we can afford a smaller complexity parameter allowing more complex trees, since the overfitting is already being limited by requiring a larger number of observations in each leaf. What that goes to show, really, is that you can't search for hyperparameters independently, because the settings of one hyperparameter will affect the optimal setting of another hyperparameter, which is why you have to do things like grid search. The result of training both of those hyperparameters is now that we have a train error of $17,000 and a test error of $21,000. That is much less overfitted. Before we had 16,000 and 21,000, so there was a bigger gap between those two, and the test has improved. So by tuning two hyperparameters, we have managed to improve the performance, although it's still pretty rubbish. Now, which variables are important in this tree? This is not as simple as linear regression, where once you had standardized the variables, you could just look at the size of the coefficients. How are we even going to decide when a variable is important in a tree? Well, one way to decide is just simply to see every single time the variable was included in the tree. That's a start. We could just look at the number of times a feature is included in the tree, but we can do better than that, because every time a split is made on a feature, the error or the loss function across the whole tree reduces by a certain amount, because otherwise that split wouldn't have been made. So we can add up all those reductions for each feature, and then we can simply list the features according to the amount by which they made the error reduce. Before we do that, can you think, is that a clever idea? Well, actually, it's a really stupid idea, because we're talking about the training data. So you can have some variables in there, especially high cardinality categorical variables, which were split on again and again and again, causing overfitting in the tree. And the reason why the MSE is reducing, or the MAE is reducing as a result of this feature, is not good. It's not because it's helping to improve prediction performance. So actually it's a horribly unimportant variable which should be removed. But nevertheless, let's print out the variable importance. According to this, what I just said about this kind of variable importance being useless is going to be very true on badly overfitted trees, where a lot of the splits are just wrong and incorrectly made. However, we have made a significant attempt to avoid overfitting, so probably these variable importances aren't completely stupid. We're going to see another method which to me seems preferable, called permutation variable importance, which can be done over the validation data, and which will give different answers and different importances, which are hopefully more reliable. But here we have it. Overall quality, we've seen that before. I think we saw that on some early linear regression models, and that was the most important feature. Neighborhood, but am I really comfortable that the living area is so far down? Well, I guess it depends what the surveyor included in overall quality. If in overall quality they included the size of the house, well then maybe it's not surprising. But if they didn't, then I'm surprised that the size features so low down. Finally, discuss, are the colors in the above chart useful? Are they? Have a think.